Oh, this is a video on Euler's theorem and how to apply Euler's theorem to solve congruences. Here is the congruence that we're going to be wanting to solve in the second half of this video. AX is congruent to B mod M. This theorem 26, which we had in an earlier video, tells us when we're going to have a solution and when we're not going to have a solution. Let's take a look at Euler's theorem. Euler's theorem is found in section 3.5. Euler's theorem states that if m is a positive integer and a is an integer that is relatively prime to m, then if I take a and raise it to the power of phi of m, I get back to 1 mod m. So for example, if we're in mod 5, phi of 5 is 4, because all the numbers 1, 2, 3, and 4 are relatively prime to 5. 3 to the fourth power is 81, and if we simplify that mod 5, I get back to 1. I do want to point out that you may get back to 1 sooner than you might expect. In other words, you may not have to raise it all the way to the power. For example, let's say a is 5. Let me get a pen here. And let's say our modulus is 12. So our theorem says that 5 raised to the phi of 12 should be congruent to 1 mod 12. Now, if we look up in our table or calculate it by hand, phi of 12 is 4. Well, 5 to the fourth power is 625, and that is congruent to 1 mod 12. But it turns out that we didn't really have to take it all the way to the fourth power. The second power would have been good enough. 5 to the second is equal to 25. And if I subtract multiples of 12 from that, I do get 1 mod 12. Since the product is 1, this means we're able to find a multiplicative inverse. Let's take a look at our handout. Euler's theorem says that if a is relatively prime to our modulus, I can take a to the power of phi of m, and this will be congruent to 1 mod m. Well, if we pull out an a here, I can conclude that a times a to the 1 less power will be congruent to 1 mod m. Therefore, the inverse of a is a to the phi of m minus 1 power. So let's calculate some inverses, for example. Let's find the inverse of 6 mod 11. This is a little bit of a trivial one, but I think it's a good first example. I want 6 to the phi of 11 minus 1. Phi of 11 is 10, so I want 6 to the 10th power. So I'm going to run this into a calculator. I'm going to get a huge number, and then I'm going to simplify that mod 11. So I'm going to jump over to Desmos and see what we get. This should be 6 to the 9th power, because phi of 11 is 10. 10 minus 1 is 9. So I need to take 6 to the 9th power. So in Desmos here, 6 to the 9th power is this huge number. Looks like it's more than 10 million. And I want to simplify this mod 11. So I'm going to divide it by 11. 6 to the 9th power divided by 11. And I get this decimal here. In order to get the remainder, I'm going to take the whole number part and subtract it away. So I'm going to have 6 to the 9th power minus 11 times the whole number portion. 916, 154, and that should leave my remainder. My remainder is 2. Therefore, 6 to the 9th is congruent to 2. Six to the 9th is congruent to 2 mod 11. And if we check this, 2 times 6 is 12, which is 1 mod 11. That was trivial. The answer is the inverse of 6 is 2. Now let's use the inverse in order to solve a congruence. Let's see what our steps are going to be. We're solving AX is congruent to B mod M. First of all, we should see if there are solutions and how many. Then to check to see if A and M are relatively prime. A and M must be relatively prime in order for Euler's theorem to apply. They don't have to be relatively prime for there to be a solution, but they have to be relatively prime in order for us to be able to use Euler's theorem. Then we calculate phi of M minus 1. We're going to be multiplying both sides of the equation by a to the power of phi of M minus 1, multiplying both sides by the inverse. So we're going to simplify so that we know what to multiply by. Then we multiply on the right-hand side and simplify that. So let's take a look at our first example. Okay, 3 and 14 are relatively prime, which means we're going to have one solution. It also means that Euler's theorem applies. I want phi of 14. Phi of 14, well, we can use our table or we can calculate it. There are 6 numbers relatively prime to 14. And I want to subtract 1 from that. This is 6 minus 1, which is 5. So the inverse of 3 is going to be 3 to the 5th power. No, it isn't. Made the same mistake. Yeah, it is. 3 to the 5th power, because it's one less power. Well, 3 to the 5th power on a calculator is 243. Now I need 243 divided by 14, because 14 is my modulus. So let's take a look at Desmos. I have 17. It goes in 17 and change. And if I subtract away 17 times 14, I get a remainder of 5. So 243 is congruent to 5 mod 14. This is the multiplicative inverse. So I'm going to multiply both sides by 5. Multiplying on the left by 5 and multiplying on the right by 5. Well, as expected, on the left-hand side, we get 1x. That's what multiplying by an inverse does. And on the right-hand side, we have 40. And if I subtract away multiples of 14, I get 12. My answer is 12. And that can be checked by substituting into the original congruence. Now let's do a more sophisticated example with bigger numbers. Solve 17x is congruent to 13 mod 60. I need phi of 60 minus 1. Phi of 60. Well, 60 has a lot of factors, so there aren't very many numbers that are relatively prime to it. That's 16 minus 1, which is 15. So I need to take 17 to the 15th power. Now, 17 to the 15th power is huge. If I take 17 to the 15th power on my graphing calculator, it goes into scientific notation and I'm losing some accuracy. So there's a number of strategies that are going to work on this, and the one that I'm going to show I'm not claiming is the best. But 15 is 3 times 5. So I could take 17 to the 3rd power, simplify that, and then take that to the 5th power. 17 to the 3rd power is 4913. Before I raise that to the 5th power, I'm going to simplify this mod 60. So I'm going to take 4913 divided by 60, like I did using Desmos or a graphing calculator, and I get 81, remainder 53. So this becomes 53 to the 5th power. And when I take 53 to the 5th power on a graphing calculator, I get another huge number. Maybe I'll jump over to Desmos and do it over there. "53 to the 5th power on a graphing calculator is 418 million. I'm doing this mod 60. So I need to take this, let's see if I can copy this. Good. And I need to divide this by 60. And I get this number and change. In order to get the remainder, I'm going to take 53 to the 5th power, and I'm going to subtract off a multiple of 60. 6969924. That's interesting. I got a remainder of 53. That's a little bit unexpected, but that's okay. So it turns out that I get 53 here. And what does that mean? 53 to the 5th power is congruent to 53 mod 60. So this is what I'm going to multiply both sides of the equation by, or both sides of the congruence in this case. I need to take 13 times 53. And I need to simplify that. Mod 60. 53 times 13 is 689, and now I just have to simplify this, mod 60. 689 divided by 60, it goes in 11 times, so I have 689 minus 11 copies of 60, and I get 29. Always a good idea to check that. 17 times 29 should be congruent to 13. Mod 60. (17 times 29 minus 13). That's 480. 60 does divide evenly into 480, so therefore this congruence is true. And here's my answer. Put a box around my answer. This has been a video on Euler's theorem and how to apply it to solve congruences. Give it a try on the practice homework. Have a great day.